Today we are going to discuss gravitation. In this we'll start with force of gravitation. What is force of gravitation and what is force of gravity? Then we'll discuss Newton's laws of gravitation. We'll also discuss Newton's laws of gravitation in vector form. Then we'll discuss what is the principle of superposition of gravitation. And we'll take different cases there where we can apply that. So all these we'll discuss in today's discussion. Force of gravitation we take as the force between any two bodies due to their mass. It can be any two bodies in the universe. We can take force between two stars, one star and another planet there. We may take a force between two stones. It may be the force between a stone and earth. So any two bodies, if you consider the force which is acting due to their mass, that will be the force of gravitation. But when we take force of gravity, this is also the force of gravitation, but in this case, one body should be Earth. Like if you take the force of gravity, in that case, it is the force experienced by a body due to Earth. It may be force experienced by a stone, or it may be force experienced by moon due to Earth. So it is the force of gravity. Next, let's take what is Newton's laws of gravitation. Newton's laws of gravitation states that the force between two point masses is directly proportional to product of magnitude of the masses and inversely proportional to a square of the distance between them. If you consider two point masses having masses m1 and m2, and they are supposed at a separation r. So the force of gravitation between the two, if we represent it by F, then F will be directly proportional to product of the masses and inversely proportional to a square of the distance between them. If you combine these two, then we'll find F will be proportional to m1 m2 by r square. If you replace this proportionality sign by a constant there, in that case F will be written as capital G m1 m2 by r square. This capital G, this is the constant of proportionality we are using here, and this is called as universal constant of gravitation. Remember that this universal constant of gravitation, this we can take there applicable for any two bodies in the universe. Whether these are the two small bodies due to their mass we are considering, or we have suppose a small body and other heavenly body, or you take two heavenly bodies, any two bodies if you consider, this constant of proportionality will be used there for all such cases. So this is a universal constant of gravitation, and the value of G is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Because here if you consider G will be how much? F into r square by m1 into m2. So if you consider this unit, then it is your Newton meter square per kg square. So that is your universal constant of gravitation. And if you want to suppose take the dimension of G, if you consider the dimension of G, then it will be your F r square by m1 m2, and we have to take the dimension of this quantity. So the dimension of force is your mlt minus 2, then it is your L square for this r square, and this is for mass, that is m1 and m2. So it is your m square. So finally it is your m minus 1 L cube t minus 2. This is the dimension of universal constant of gravitation. Remember that the force of gravitation is attractive in nature. Other forces if you consider, like you have suppose electrostatic force, magnetic force, they are of both types. It may be your attractive as well as repulsive. Force of gravitation is only attractive. Suppose we want to define this universal constant of gravitation. Now for that, what we can do, if we consider that if m1 equals to m2 and that is equals to 1 unit and r is also say 1 unit, then what we'll get? We'll get f equals to g in this expression if m1 and m2 both are equal and this r is also say 1 unit there. So in that case, f will be equal to g. We have taken m1 and m2 both having 1 unit value, r is also 1 unit, then in that case f will be equal to g. So we can define universal constant of gravitation as the force between two unit masses placed 1 meter apart. So this is numerically equals to force between two unit masses kept unit distance apart. So that one, if you calculate and measure it, in that case you'll get that this universal constant of gravitation or the force experienced by unit masses placed 1 meter apart there or unit distance apart, that one will be as 6.67 into 10 to the power minus 11 Newton per meter square per kg square if you are taking all these in SI. That means mass is 1 kg, distance is 1 meter, then you will get that particular value. Let's now take Newton's law of gravitation in vector form. So for this, what we do, suppose we take point 1 and 2. These are the 2 points where we have the masses m1 and m2 located. These are the point masses, suppose, and they have the position vector r1 and r2 respectively. R1 is the position vector for m1 and r2 is the position vector for m2. So now if I consider that F12, this is force experienced by m1 due to m2. So it is the force experienced by m1 due to m2. So this term in magnitude, what we can write? It is g m1 m2 by square of the distance. What is that distance? It is the distance from point 1 to point 2. And suppose if I take the direction, the force will be attractive between m1 and m2 because it is a gravitational force and it is attractive in nature. So it means this one will be having its direction as r12. Suppose I represent it as this. This is a vector from 1 to 2. So the direction of the force of this one, that is your F12, will be also in this direction. So F12, if you consider, it will be in this direction. So this will be R12 vectors magnitude whole square and direction is in the unit vector direction R12. Because it will be in a direction 1 to 2. It is attractive. So it will be like m1 will experience force towards m2, m2 will experience force towards m1. So this is the expression. Now you know that from vector law, if you consider, so from vector's law of addition, what we can write? R1 vector, that is this vector, plus R12, this is equals to R2 vector. So that means what we can write? R12 vector as R2 vector minus R1 vector. Final vector minus initial vector. So this is your R12 vector. Now here, if you consider this R12, R12 can also be written as your this R12 vector magnitude whole square and unit vector can be written as your R12 vector divided by its magnitude. Because the unit vector can be represented as vector divided by its magnitude. So here if you consider this F12 what we can write? G m1 m2 by r12 vector magnitude whole cube, and this is your r12 vector. And this what we can write? Again, substituting this one, this will be your G m1 m2 divided by r2 vector minus r1 vector. It is r2 vector minus r1 vector, and this is basically its cube. So this is the expression for F12. Similarly, if I take, suppose, the force experienced by M2 due to M1. So that force will be in which direction? It will be your, first of all, it will be represented as F21 experienced by the body due to the other body. Like if it is your F21, it is the force experienced by M2 due to M1. And what will be its direction? Its direction will be for R21, from 2 to 1. So if I take similarly F21, this is force experienced by M2 due to M1. And what we'll write for this one? In the same way, if you just substitute, it will be your G M1 M2 divided by R21 vector magnitude whole square, R21 vector, that is the unit vector there. And if you substitute, it is your G M1 M2 by R21 vector magnitude whole square into R21 vector by R21 magnitude. So it is once again R21 vector divided by R21 vector magnitude cube. So that one, if you substitute, it is G M1 M2 by R21 vector magnitude whole cube, and this is your R21 vector. And now if I'm substituting for this one, what I will get for F21? F21 will be G M1 M2 by, just it will be now C, R2 plus R21, that will be your R1. So now this time it will be your R1 vector minus R2 vector. R2 vector. This will be the expression. So this is your second equation. Now you can easily see how we are getting this one. Here you will find that this one will be R2 vector plus R21 vector, R2 plus R21. This is your R1 vector. So R21 vector is how much? R1 minus R2. This is the expression. So this is what we have substituted here. Now, the most important thing, if you just try to see that magnitude of the vector R12 and R21, that will be equal, because from 1 to 2, whatever is the displacement or the distance there, magnitude wise it is same as 2 to 1. So here what we have, R12 in magnitude, this is your R21 magnitude, but of course direction wise it will be different. So here if I just substitute, what I will get? G M1 M2 divided by R2 minus R1 magnitude whole cube, and I'm changing the order. So if you change the order, there will be negative sign introduced here, and then it is your R2 minus R1. Now you can see this entire term is nothing but it is your F12. So this term, this is equal to minus F12. So what we have got, F21 is equals to minus F12. So we are getting that F21 equals to minus F12. This shows that Newton's third law is also obeyed here. Whatever force one body is experiencing, the other body is also experiencing same magnitude of force, but direction is opposite. So you can easily show that Newton's third law is also obeyed here in this case. Principle of superposition of gravitation. What is that? Principle of superposition of gravitation states that the resultant force experienced by a particular point mass due to a number of point masses is equal to vector sum of the force due to individual masses on that. So that means, suppose I take that force, resultant force experienced by one particular point mass, and on that we have different point masses exerting gravitational force. So suppose F1 is the gravitational force exerted by a particular mass, say M1. There is another one that is exerting force F2. Like here you can assume that you have mass M1, M2, M3. All are exerting force on a particular point mass. Suppose this particular point mass is here M. This one is experiencing force due to this one as F1. Due to M2 it is experiencing F2. Due to this it is experiencing F3, and so on. So the resultant force which this point mass will experience, that will be given by the vector sum of the forces due to individual point masses on that separately. F1 is the force exerted by M1 on this point mass. F2 is the force exerted by M2 on this particular point mass. Similarly, F3 another. So resultant force experienced by this point mass will be given by the vector sum. And there will be a number of questions, numericals based on this. Remember, for all such cases that you have to take the vector sum. Normally, we calculate what is the force of gravitation due to a pair of masses there, say between M and M1, M and M2. We have calculated. But when we have to find the resultant, we normally just add it. It should not be a normal algebraic addition. It is a vector addition, because this is a force which is a vector quantity. So obviously it will be given by vector addition there. Let's take some conceptual type questions based on this Newton's laws of gravitation. One question which is often asked, who exerts greater force of gravitational attraction? Earth on Sun or Sun on Earth? Here, suppose I assume that this is Sun and here we have the Earth. You have to tell who exerts greater force of gravitational attraction. There will be gravitational force of attraction between the two. So the question is, who is exerting greater force? Earth is exerting greater force on Sun or Sun is exerting greater force on Earth? Mass, suppose if I represent mass of Sun is ms and this is your me. And if you consider the separation between them from the center, suppose it is your r. Now here, because everyone knows that the mass of the Sun is very large as compared to that of the Earth, so many times it gives the impression as if the Sun is exerting greater force. But this is not correct. Force experienced by Earth due to Sun. FES is the force experienced by Earth due to Sun. So this is your G, mass of Earth, mass of Sun by a square of the distance. That is your R square there. If I consider the force exerted by Earth on Sun, so we can write it as your SE, experienced by Sun due to Earth. So this is your G, mass of Sun mass of Earth square of the distance. Of course, the direction wise, if you consider, for the force experienced by Sun, it is directed towards the Earth, and for Earth it will be directed towards the Sun. So direction is opposite. But now if you look at the terms on the right side, both is same. So in that case, force exerted by Sun on Earth, that is the force experienced by Earth due to Sun, is same as force experienced by Sun due to Earth. So both are exerting the same amount of force on one another. Of course, from Newton's third law also you can easily say, if you consider the force between the two, they must be exerting equal force on one another. Magnitude wise it will be equal, direction will be opposite there. Another question, again in continuation of this, is asked, like if the two are exerting the same amount of force on one another, why is it that the Earth is revolving around the Sun and not the Sun around the Earth? So here, if you just consider this one, that the force what we are taking, this is equal. And what is force? This is mass into acceleration. So if you consider now that this is, suppose I write it as your F. So here, if you consider, this is given will be mass of Sun to acceleration of Sun. And for other case, it will be given as mass of Earth and acceleration of Earth. So both is experiencing same force. Now you can see that the acceleration term, if I write, it is your F by ms, and here it will be acceleration of Earth will be force divided by mass of Earth. Now since the mass of Earth is very small, so acceleration of Earth will be very large. So here we know that the mass of Sun is very large as compared to mass of Earth. Therefore, acceleration of the Earth will be very large as compared to acceleration of the Sun. And that is why the Earth is revolving around the Sun and not the Sun around the Earth. But do remember one more thing. It's not that exactly at the center of the Sun is the center of revolution of the Earth is rotated. Basically, both revolve around one another. That means basically about their center of mass. So it will be, that means Sun is also not a stationary. It is also revolving, and its orbit has the center, which is the center of mass of Sun and Earth. Similarly, Earth is also revolving around the Sun, not exactly with Sun at its center of the orbit, but center of mass being at the center. So what will happen? Basically, mass of the Sun, as it is very large as compared to that of the Earth, and you know that the center of mass is shifted more, or it is basically located more closer to the body of heavier mass. So that is why the position of the center of mass for this system will be very close to the center of the Sun. That is why it just appears as if the Earth is revolving around the Sun and not the Sun there, and it appears to be stationary. There will be definitely its orbital motion there, or its motion there about the center of mass. But since center of mass of the combined system is located very close to the center of the Sun, so it is not noticed in a prominent way. Suppose we take another question, and it is said that we have 2 point masses m1 and m2. They are located at a distance d. Where should a third mass should be kept so that the net force on the third mass is 0? So where we have to put the third mass? So suppose the third mass is your m. So let's suppose that it is at a distance x from the first mass, or m1. So the force experienced by m due to m1, that will be your m1. This is equals to m1 divided by x square. And Now its distance from the other mass, it will be your d minus x. So the force experienced by m due to m2, this is your g m2 by d minus x whole square. Now it is given that net force on this mass is 0. So for net force on m to be 0, this Fm_m1 must be equal to Fm_m2. So that if you substitute, it is your gm_m1 by x square. This is your gm_m2 by d minus x square, or d minus x by x. This is your m2 by m1. So that gives you d minus x by x equals to root over m2 by m1. Or what you can write here, you can write the d by x minus 1 as root over m2 by m1. So from this we can write d by x equals to 1 plus root over m2 by m1. And in that case, this will be your equal to root m1 plus root m2 by root m1. This is d by x, or x is equals to d root m1 by root m1 plus root m2. So this is the expression for the distance of the location of the point mass m, so that it does not experience any net force. So this will be the expression. Let's take another case. Suppose it is given that we have 3 point masses m located at the corners of an equilateral triangle of side A. This is suppose your A, B, C. You have to find net force experienced by the mass kept at point A. So again, this is very simple. If I consider the force experienced by mass located at A due to the mass of C located at C, or force experienced by this mass due to the mass at point B. So suppose if I take force experienced by A due to C, this is how much? It will be your g m by x square. That means it is your A square here. And what is its direction? It is in this particular direction. Similarly, if you consider, that means I can write this is along AC, this vector. AB, if I consider, this is your gmm by A square. This is along AB. So the net force on particle at A, that will be F equals to root over FA C square plus root FAB square plus 2 times AC FAB into cos of the angle between the two. If it is an equilateral triangle, that means this angle is 60 degrees. So it is your cos pi by 3. So that you can substitute. So this will be how much? This is basically g m square by A square. That term we can basically take outside. And so here what you will be left with? It will be first 1, it is also 1, and this is your half, and this power is your half. So this is your g m square by A square. Similarly, as an extension, if it is given that we have 4 point masses, suppose this is your m1, this is m2, this is m3, this is m4. located at the corners of a square of side A. You have to find the net force experienced by mass at A. So for this, again, I can take that it will be force experienced by M1 due to M2. So it is your F12 direction. This is your F13. This is your F14. So these are the forces there. Now F12, if you have to take, this is how much? G M1 M2 by A square. And for this type of force, if you have to calculate, it is better if you represent in Cartesian form. There your calculation part will be easier. So this is the force, and this is your along x-axis. So this is your, suppose, I cap. Similarly, F13, this is also equal to G M1 M3 by A square. And now it is just midway because it is a square there. So it will be midway. So it means it is your at an angle 45 degree with x-axis. So it is your 1 by root 2I plus 1 by root 2J. That will be the component there, because it is basically F cos 45 degree along x-axis. So this is your F cos 45 is 1 by root 2 along x-axis. This is along y-axis. F14. Oh, this will be equals to G M1 M4 divided by A square, and this is along y-axis. So the net force, this is your F12, F13, F14. You can just take the sum. Here you just add x component at one place, y component at one place, and then you find out the magnitude. Because it will be there in Cartesian form, I cap term into I cap plus y component into j cap. So from that you can find the resultant. But do remember that they are the M1 is common term, but it is your M2, M3, M4. These are the different terms coming in the different expression. So that way you can easily find the force there experienced by any given mass. So this is how we apply superposition principle here.